Um, right. So just got 23 questions, and let's just get started. Right, question one. Question one is find the function's domain and the function's range. Describe the function's level curves. Find the boundary of the function's domain. Determine if the domain is an open region, closed region, or neither. Okay. Decide if the domain is bounded or unbounded. So you have okay, square root of y minus x. We want the domain of this function. So it's a multivariable function, and so the domain would be that y minus x is bigger than or equal to 0, which is to say so all such coordinates, right? If I had to draw it in the xy plane, it would be something like this is the y equal to x line, this is everything lower, this is everything here. So this whole shaded area along with this whole line. So this is a closed region, right? Because the boundaries are also included. So describe the function's level curves. So it's square root of y minus x, right? Okay. So for example, for z equal to 0, this will just be the y equal to x line. Then for the, so I'm just gonna copy that in fact. So I'm gonna make some markings. So basically y minus x equal to z square. So like this is for z equal to 1, then for 2 it will be like square of that. So this would be 1, this would be 2, 3, 4. So this is one value, this is the other value. 5, 6, 7, 8, 9. I suppose this is what other value will be. So alright, so this is the first contour. For -1 it doesn't really make sense, so let's not go with that. So this is 1, 2, this is 3, this is 4. Okay, and this will be 5, right? So 1, 2, 3, 4, 5, right? This is going to be 9. Cool. So these are the level curves. I'm just going to shade this a bit, just like for the sake of it, but I guess you got it pretty much. So something like this. Sure. So that's what A is. So A is done. The domain is, I mean, I don't know how to exactly write this whole thing like y bigger than or equal to x, but I'm just going to write this as a set. So it's all xy such that y is bigger than or equal to x, right? Where obviously xy is in R2, right? So I should probably write that over there. So this is in R squared such that y is bigger than or equal to x. Cool. This is closed. And what else did we want to find? Right. So is the domain bounded or unbounded? So I've, oh, okay. So the domain is just a set, and so a bounded set is something whose, yeah, okay. A bounded set would be something which is like constrained by this thing. So basically, if you take any 2 points, the distance between them is less than some fixed distance. When I say distance, it could be any sort of norm, but in this case, I'm assuming it's the Euclidean norm. So this is an unbounded domain, closed, unbounded. What else? That's pretty much it. Question two. Question two is once again the same stuff. The level curves, find the boundary of the. Okay. Right. So you just have f(x) equal to xy. So this is like defined everywhere. So the domain is obviously all of R2. This is, yeah, right, the function's level curves. So hyperbole. So xy equal to, so this will be like the first thing, like z equal to 0. For like z equal to 1, this will be like passing through 1 1, so it's something like hyperbola. So it's just going to be like a bunch of different hyperbolae, all of them just, so I'm just going to copy this in fact, just draw one of them really nice. So this will be 1 comma 1, right? Right. So whenever x is equal to y, that line that passes through square root z comma square root of z. So for example, if z equal to 2, this will just be like somewhere over here, right? Yeah, suppose. Okay, I should probably do this correctly. So this will be 2, this is 1.4, this is 1.7, so this is where square root 2 is, square root 3 is here, over here as well. This is square root 2, this is square root 3, something like that. So square root 2 would be over here, and square root 3 comma square root 3 would be somewhere over here, so something like that. Okay, so it's 1, and then this would be over here, and then it just gets progressively less and less bit, basically. And sort of 4 would be 2, which is like very much over here, and so on. So that's pretty much how the region is. Yeah, I have no idea how I would like exactly tell you like how this region is, but just take my word for it, I suppose. Okay, I also probably have to reverse all of this, so just give me a second. And I'm just gonna copy the whole thing, like it doesn't really hurt. I wonder if I can actually reverse this. Can I? Oh, I can't. Well, that's not a surprise actually. Sure, I'll just have to. This really sucks, but fine. I mean, it's not a big deal. Whatever, however bad this is, at least you know. But right, this is okay. Fine, and so this one is supposed to be somewhere over here. Am I right? I think so. Okay, paste it again, and this is supposed to be 2 comma 2. So this is what the level curves look like. I'm not gonna shade this, like I don't have that much of time. That's question 2. Okay, the domain is like all of R2, and since it's that, it's like not closed, it's not bounded anything, because there are no boundaries, so this is unbounded. And so the question is this a closed region? That's a very good question, because over here you don't actually have any sort of boundaries. I think, yeah, the way we defined closed was that your limiting points are also, so basically the boundary points, those are also in your set. And so in this case, obviously the limiting points will be in your set. I guess the limiting points are like infinity comma infinity. Are they in the set? Yes, I suppose yes. Because if they're not, then even this thing would not be a closed set. Right. That's a good question. Is any infinite set basically just unbounded? Basically not closed or something, because we know that the R set is pretty much just given by this interval, and we know this interval, we don't usually say it's a closed interval, so this should be an open interval, because the concept of infinity does not lie in R2. That's a valid thing. So I'm gonna go with open, although this is kind of a, so in that case this would also be open. I actually just searched this up, so I mean I feel this is probably going to be open, but sure. So is R2 open? Is R open or closed in R square with respect to the standard topology of R? I don't know what's going on. Not even a subset of R square. I have no idea what's going on. Okay. What is the definition of an open set in R2? Okay, this is this is nice. No, wait, actually just search up a definition, right, and that will tell me everything. So open set. open domain on I'm just gonna go with set open set in R2 does not contain any of its boundary points, but there is no boundary if it's going to infinity infinity. Mm. uh, are unbounded sets open? I think they are. The entire real line is unbounded, open, and closed. What the? Okay, this is very weird. The definition of compactness reduces to bounded and closed, but in general may not. For okay, sure. What? Set A is open if for every point A of A we can draw a tiny ball around A and all the points in the tiny ball will be in A. Can you do that um, for this thing? Yes, you can. So what would that mean? So that would mean this is actually open, right? Yeah, that actually makes sense. So there would always exist some ball such that this actually happens. So sure, it's open. In this case, that wasn't the case. Like you take anything on the edge, you can never do that. You can never draw like a tiny ball and then hope that it will be entirely contained in the set. It's just not going to happen, right? So this would be in fact closed. Okay, so closed is more of a restriction in fact, because like if it's extremely weird. Oh, so this is supposed to happen for every point of x. Right. A set A is open if for every point A of A we can draw a tiny ball around A and the points in the tiny will be in A. Right. Oh, so the definitions are completely different. For openness, it's that this tiny ball stuff, and for this, it's like all the limits are also okay. Sure. So, for example, 0, 1 is not closed. Sure. The only points that must lie it even with form also. Okay. So, are these the opposites of each other? Can something be open and closed at the same time? And I would say yes, it probably can be. Consider the real numbers. Every single limit would be there, right? If the limit exists. Um, yeah. Oh yeah. What about this one? The empty set is closed. So once again, the definition of closed is that every limit would also be in the set. Now in the empty set, there is no sequence to form. So what limit? What are you even talking about? Yeah. They're using the different techniques. I don't know what they're talking about. They are first using this. So all they're doing is they're showing it's not open, right? Can't draw a ball around them that there isn't. So the empty set is open. What? Okay. The empty set is both closed. Okay, because the definitions are orthogonal. They're not. I mean, they're sort of independent. They're not like one implies the other is not going to happen. Okay. Not all sets have limit points. For example, take Z. If you take any real number, you can draw a small ball around it and not hit any integer. Sure, we can. What about if it is on an integer? Okay, so no point is a limit point of z. This is extremely weird. This is extremely weird. I have no idea. But by this logic, what should happen is that you would just say this thing is closed and open at the same time. So this is closed, open. So basically, it's closed at this edge, open because you have the usual definition. Wait, what? No, it's not open. Is it closed? Yes, it is closed. It cannot be open, right? Because we have this edge sort of a thing. So it's not open. I think it's something like when we say open, we mean open on all sides. So it's closed and unbounded. What about this one? Um, this is unbounded, open and closed at the same time. This is extremely weird, but well, whatever. Because well, yeah, the set of everything, a universal set that's also closed and open at the same time. So I have no idea what's going on with this terminology, but hey, that works. Question 3. I just really have to check with people to see what's going on, but whatever. Fine. So level cursor for the easiest part in this. I really don't know how to deal with these definitions. Anyway, so you have 16 minus x. Okay, so this will be nice because for this to make any sense, what should happen is that 16 minus x or minus y square, that should be strictly bigger than 0, right? Which means that x square plus y square is strictly less than 16, which is basically a circle. It's this circle. Yeah, easy, right? So if we set this equal to like z, this would be just, this will be equal to 1 upon z square. So basically like x square plus y square, it will be equal to 16 minus 1 upon z square. So like consider z equal to 0. Z equal to 0 is just boundary. Z equal to 1, it's slightly less, and so on. Sure. Okay, so as z gets smaller and smaller, this thing gets bigger. So for z equal, oh wait, what? Z equal to 0 is really messed up because, so this will be z equal to infinity. Okay. So that's never going to be happen because z equal to infinity is not allowed, right? So this will be what? An open set, because no matter what point you take, you can always draw a ball around it because it corresponds to some z, right? And you have a z more than that, so that works. So it's an open set, and the contours will just be like that. Let's try to draw the contours. Let's also actually draw some pretty lines. I said pretty lines. Oof, I don't know how to use this. That's the only, okay, I have forgotten how to use this. Good, that's how it should be. Okay, that's my pretty circle. So this thing is 4, this thing is 4. It doesn't really look like this is aligned, but whatever. This thing would be 4, this thing would be 4. We would want to know where this is going to be 3. So it's equal to 9, 9 equal to 16 minus of 1 upon z square. So it's like what? 7 equal to 1 of 7 over 1 upon z square. So like z equal to square root of 7. That's not the way to keep going. So first we'll just be like, this is z equal to infinity. Z equal to 0 is really messed up. You do not want that to happen, right? So z equal to 4. Z equal to 4 is where you have 0. So this thing is z equal to 4. When it's 3, it's 1 by 16 minus 1 by 9. Huh. What? When it's 3, oh, you can't go lower than 4, right? So z is like less than or equal to 4. Sure. What happens when z is so you also have to find the domain and range. Yes, functions range as well. Over here as well I have to find the range. So in this thing, range was just square root of 1 so it's like just some positive number or 0. So domain is just this stuff. So I'm just gonna like draw this whole thing like like a mapping. So it's going from this to the range. So the range would just be everything that's plus, so non-negative, so greater or equal to 0. That makes sense. Over here, is going from R2 to R2, I suppose, because you make y equal to 1 and then you pretty much get everything. So it's like just going from R2 to R2. Shouldn't be too hard to see. Cool. And then we also have to see if the domain is, so we don't have to do anything for the domain. Also, you have to find the boundary of the functions domain. Now that's not a big deal. It's a easy thing to do. So here the boundary would just be like y equal to x. Over here the boundary would just be x square plus y square equal to 16, like when z equal to infinity. Yeah, that kind of makes sense. Okay, so z equal to 4 gives us this point. Z equal to 3 would be like on 1 upon, okay, 5. That would be like 1 upon 60 minus 1 upon 25. So 1 upon 60 is like 9. 9 upon 16 minus 25. Square root of that would be like 3 upon 4 times of 5, which would be, yes, which should be just 3 upon 20. So 3 upon 20 is like 0.3 by 2, so 0.15. 0.15 would be something like this. So that's actually a very small circle. Okay, next you have z equal to 6. So that would be something like what? This is just really bad. I did something really messed up, didn't I? Yes, I did. It shouldn't be like this. It should be 16 minus 1 upon 25. Okay, something is really bad. This is supposed to happen at z equal to 1 upon 4. I am stupid, am I not? Right, in infinity you sometimes just have 16. 1 upon 4 you have 0. Okay. What about z equal to half? At half you just have 16 minus, so 2 squared 4. So just have like 12, sort of 12. Just like 2 square root of 3, so like 2 times of 1.7 something. So that's something like 3.4. Okay. Okay, that escalated pretty quickly. 3.4. Something like that. Yeah, that's probably good. I should just increase it a little bit. Okay, this is the first thing. So this is z equal to half. So 0.5, this thing is 0.25. Okay. Next, what we want is for z equal to 1, I suppose. No, that's not a way to do. Z equal to 3 by 4 is next thing. So this is 16 minus 16 by 9. It should be something like 16 times of, so 9 minus 1 is just 8. 8 upon 9. So take a square root of that, huh? So 4 by 3 times 2 square root of 2. It's like 8 square root of 2 upon 3, which I actually don't know what that value would be, but like 8 times of 1.4 is 8 times of 32, which is 1.12 upon 3, which is something like so 3, 9, and then 0.1. Oh, that works wonder. 92, right? So 0.7 and then was like 3, 3, 4. So very close to 4 in fact. 3.7 something. Yeah, that was 2. That's not what you wanted, right? Yeah, you wanted 3.4. So 3.4 is way far ahead. I suppose that looks like 3.4. This is I'm just really guessing everything. Okay, this is exactly 3, so I'll make it like slightly. So this is 4, 3. Okay, this is another thing. I think this is in fact 3. So it'll be 2. So it'll be 1. Yeah, sure. So 3.4 would be much bigger. Now this is a circle. Okay. Okay. So you're telling me everything will have to be squeezed between this much of space. How am I supposed to draw that? Oh, I know. I'll just, yeah, that works. Yeah, that actually works wonders. suppose this is how it's going to be, and so on. So these are my contours. This is really messed up. Yeah, but that's just how it is. I'm going to draw one more contour just for the sake of it. Okay, this should be okay. Yeah, okay, just move on. So this is how it's going to look. This is really weird, but anyway, move on. I mean, we know what this is. It's like it's a top of a sphere with radius like 4, but it still looks weird. That's the problem. Question 3, question 4. Oh, so I also have to do that stuff. So this is going from what to what? This is going from this region open domain thing. Oh, this x plus y square has to be like strictly less than 16. It's going from that to whatever z can take, all the values. So yeah, 1 upon of that. So like 1 by z takes all the values, like this is extremely weird actually. Think about it. So anyway, z takes like what sorts of values? So 1 by z, that lies in this interval, so it's going all the way till what, 4? So it's 0. Okay, am I doing it correct or not? So you can't have 0, so it's impossible. Yeah, okay, that makes sense. So this will just be like 1 by 4 to infinity. Sure, next thing. Question 4 is find the functions domain and functions range, describe the functions level cost. It's the same thing again and again. So sure. So what we'll do is just have this z dash thing. Z dash is just x plus y square minus 1. This has to be bigger than 0. 0, it doesn't make sense. So it's strictly bigger than 0. So you just have to have. So we'll just put a 1 over here. Alright, that's how it works. This is the boundary. Oh, so you also have to do this, right? Is this open, closed, or what? So the domain, this thing is certainly open and it's bounded, right? This one as well, it is actually, so it's unbounded because it has to be bigger, so yeah, it's unbounded. Yeah, so heck, what was I doing? Right, so natural log of that. So this is going to be like e power of z, right? So that's strictly bigger than 0, obviously. Yeah, so z can be anything. It just can be anything that we want. Make it infinity to infinity, everything's allowed. So we'll start at z equal to 0. At z equal to 0 is just like e power of, so 1. So it's like x plus y square equal to 2. Yeah, which gives us like square root of 2 as the thing, as the radius. Okay. I'm getting some really bad feelings from it, but whatever. Square root of 2, it's like 1.4, so it's somewhere around this. Cool. Right. So this is what this thing is, the boundary condition. I'm gonna change the style, whatever, that works. So this is z equal to heck, this thing is 4, this thing is what? Okay, something is messed up. So this is z equal to 0. Yeah, Okay, so that's 0. What about 1? It's like e power 1 minus 1. So e plus 1, the square root of that, that's the radius. What would that be? E is something like 2.7, so that becomes like 3.7 something, so sort of that. The closest I can think of is, heck, no, no, 3, close to 3. Not good. What's 14 square? 14 square is like 196. 15 is 225. No, 17 is. I haven't like forgotten what the thing was. It's like 400 minus of 120 plus 1. It's like 3, so I got 281. Yeah, that's 17 square. Sure. Hey, is that correct? Something is not adding up. Never mind. 18 square, that's going to be like 400 minus, so root of that is like 4, so just 80 plus 1, which would be something like 3, not 1. Oh, here as well, it's supposed to be 9, sorry for that. That actually makes sense. This would be 4, so just 324. 324 is close enough. No, still gotta go big, so 19 square, and this was 361. 361 is actually close, and 20 sort of like 400, too much. So this is something like 19 to 20 thinged. Yeah, I should say 1.9 to 2 sort of a thing. So it's very close to 2. That's all we really care about. Okay, now I know I really haven't marked the correct place, but whatever. So this is how it's going to be, and then what? So close to 2, and then we would want z equal to 2, so it's just like e squared plus 1 square root of that. Okay, I don't know what e square is. I think 27 square wouldn't be such a big thing, so it's like what, 900 minus was 60, so it's 120, 120 plus 9, I suppose. It's like what, 8, and then what, 7, 7, 8, 9, 7, 7.89 is more like it, square root of that. Oh, that plus 1 obviously is like sort of 8.89. Interesting. 8.89. It's something like, okay, no, don't do that. 8.89. If I take a 2 outside, so it's just 2, and then you got 4 outside, so it's like just 2.2, 2, and then 1 is like 5, so whatever. So close to 2.25, I would say. I mean, slightly less than that. And that's, so 1.5 square, so just that's a 1.5, so it's something like 3, which, okay, that's not a big surprise. This is very close to 9, so sure. So it's less than 3, that's all we care about. Right now it's growing very much just linearly, but yeah, we'll have to see. I guess this works. Yeah, I guess this works. So it's just a bunch of concentric circles, but like, how is the gradation? I have no idea, but you know that it's natural law of, so you can just figure out derivatives, right? Yeah. So right, what was this? X square plus y square. So x square plus y square equal to 1 plus e power of z, which is equal to r square. So basically r is the square root of 1 plus e power z. So as z increases, your r dash, which is the derivative, that's something like 1 upon 2 square root of 1 plus e power z, something like that. So what happens to that? So you take it inside, it's like very conjugation. So okay, just what? Am I doing this correctly or not? I would never know. So just e power negative 2z and then plus e power negative z. So basically, as It increases, this stuff decreases, but this whole thing increases. So your change in radius is like increasing. That doesn't make sense. Are you sure about it? I mean, yeah, that's how it should be. It increases over time. So this is going to become like exponentially, so order e power z by 2, right? So this will actually become like much bigger as we keep going. So I'm guessing this is like more than linear, something like that. I'm just gonna guess it, something like that. So just move on. Okay, so once again, what's the domain and range? So this is going from R2, so that's not R2 actually. So it has to be bigger than 1, right? So it's all x, y such that sorry for that, such that x square plus y square is like strictly bigger than 1. So it's an open set, and it's going from that to whatever is the range, which is everything pretty much. So just all of R. Yeah. So this thing is an open unbounded set. Right. Next. Question 5. Question 5 is find an equation for and sketch the graph of the level curve of this function. Square root. Oh, come on, give me a break. Is this the same thing again and again? I don't want to sketch these graphs. It passes through the given point. Huh? Oh, so just one of the level curves is passed through this point. Okay, sure, that shouldn't be hard. So at 3 comma minus 1, what is z? It's just square root of 3 plus what? I square is just 1, and then that minus of 3, which is like 1. So basically z equal to 1. So you just have to have 1 equal to x plus y square minus 3, which implies x is equal to, what was I going to do? I was going to do something, I kind of forgot. Oh yes, it is equal to 4 minus y squared. Sure. Looks familiar. Well, never mind. So just 4 minus y squared. So you know how to graph y equal to 4 minus x squared. You obviously know how to graph this thing as well. So at y equal to, this is 1, this thing is 2, this thing is 1, this thing is 2. That didn't go so well. So at y equal to 2, what would happen is it's just like one of these zeros. As y increases, this becomes more and more negative, so your x would be in the negative side. So it's something like this. So at y equal to 0, just have x equal to 4, I suppose. So that would be 1, 2, 3, and 4 over there. And that gives us the parabola we are looking for. Yes, this is really good. So that's your level curve. Okay. So what about it? What do we want to do exactly? Oh, that's it. That's the whole question. Question 6. Question 6 is sketch a typical level surface for the function f of x equal to natural log of x square plus y square plus z square. So this is a 4-dimensional thing. I have no idea. Okay. Oh, this is weird. Fine. How do I sketch a surface like in 3D? What are you talking about? I mean, the typical level surface is a sphere, yes, but how am I supposed to show you anything? Like, I mean, this is just one of the level surfaces. You would need many to be able to understand what's going on, and I don't think you can see a sphere inside a sphere. That doesn't make sense. So fine, I'll just draw this sphere and be done with it, I suppose. Yeah, so I just like set z equal to what, 0, sorry, w equal to 0 or f equal to 0, that's right. Okay. So it'll just be like 1 1 1. Easy. 1 1. Actually this is like over here, 1 1. This thing over here is like 1, this thing is 1, this minus 1, but sure, so you can say it's minus. So this is like x y and z, this thing is 1, this thing is -1. Yeah, that pretty much does it. I guess I could draw something like this. Yeah, I'm really not going to be doing some artwork over here, but I have to show you that this thing is like, what do we call it, like, it's a 3D thing. So sure, this actually works out, I suppose. Okay, next question 7. This was really bad. So this is z equal to 0, so w equal to 0. Find an equation for the level surface of the function. Why do you want me to do this stuff through the given point? Sure, I'll do it. I'll do whatever you want to, but the serious question should be why should I do this? This is 1 plus 1 plus 2. Wow, 4. Amazing. It's a sphere of radius 2. Never thought anybody could come up with this. You know what, I'm just copying like the previous thing. I'm not spending effort doing this stuff. Okay, this is turning into a nightmare. I thought I would be getting good questions. I'm just getting bullshit. So this would be now 2. Yeah, sure, move on. Question 8. Question 8 is, oh yeah, okay. Find this limit. Limit as x y tends to 0 0, cosine of x plus y. Okay, cool, whatever. So this thing tends to 1, this thing tends to what? 0 0, it's just 1. Do I even have to do anything? No. Okay, I should be doing this with the epsilon delta definition. I hate all of this. Is there some better way? Oh, you can use the quotient rule, right? So you can say that, okay, it's just the limit of this stuff upon the limit of that stuff, and then you can use the chain rule and say, okay, it's just the limit of cosine of, what is the limit of x plus y cube, which, I mean, it does converge to something, and we know that x plus y cube, it converges to 0. So cosine of 0, 1, and that exists. This is also existing, so just 1. I'm just gonna move on. Find the limit by rewriting the fractions first, whatever. So just square root of 2x minus y minus 2 upon 2x minus y is 4. It's a classic thing. So just 1 upon square root of 2x minus y plus 2, whatever. Just put x equal to 0 in this. You just get 1 upon 2. Easy. Oh wait, okay, what? X equal to 2, y equal to, so y is small, y is small. What that means is this 2x minus y thing is always going to be positive no matter however you approach this. Sure, so it's always defined at least. Yeah, and 2x can so this stuff 2x minus y can never be equal to 0. So okay, that's, I mean, obviously, and at the same time this 2x minus y minus 4, I mean, that is actually going to 0 in a way. This is bad. Why do I feel this is tending towards limit does not exist, something like that, but I have no idea. Whatever, just do it mindlessly. This will be like 1 upon, so this actually implies it's 1 upon what, 4, just 2 plus 2, it's like 1 by 4. So if the limit did exist, it would be 1 by 4, but the question is, does the limit actually exist? Think. Okay, so you can rewrite this whole thing. So you can rewrite it as square root of 2x minus y. So I'm just going to say x minus 2 is t. So this just becomes something like 2t minus y minus x minus 2, just like plus 2 over there, minus 2 upon what we would just have t minus y. Yes. So now it's like as t and y approach 0, stuff happens. That's the question. Oh, it's supposed to be 2t minus y. So in fact, let's just say 2x minus y is something. Let's just say that 2x minus y is z. So this just becomes like limit as z tends to 4, because yeah, because it doesn't matter what path you take in game, this is what is going to happen. So just square root of z minus 2 upon z minus 4, and this limit does exist, so it's okay. It's okay. Yeah, so I mean, whatever path you are going to take towards your point 2 comma 0, the fact is, so this is the point, so let's say this path, the fact is that whatever is happening to the value 2x minus y completely determines this limit, right? So yeah, I mean yeah, this limit will actually exist. It's crazy, isn't it? Despite all of this bad stuff, it actually will work out. What about the point where, like, 2x, so this function's domain is where we should be for this to even make sense, and this function's domain does not contain any points where 2x minus 5 equal to 4, because there is like undefined. So yeah, sure. Question 10 is fine. I really just have to look up how to formally prove this, because if it does come in the exam, I'm seriously not going to be able to do anything. Find the limit by rewriting the fractions first. Limit as xy tends to 0, 0, 1 minus cosine xy on xy. Rewriting the fractions. What are you talking about? Oh, I got it. So it's just going to be like what? 1 minus cosine times of 1 plus cosine upon 1 plus cosine times of xy. And this just turns out to be like sine square upon xy. And that times sine square of xy, obviously. That is 1 upon 1 plus cosine. So this thing tends to, so as xy tends to 0, 0, this thing just tends to 1 upon 2. And this thing tends to 0 because sine upon xy, remember kids, it's tending to 0. So it's tending to 1 because of the sine x upon x limit. And sine x is tending to 0. So this is in essence is tending to 0. Not a big deal. Once again, the reason this is working out is we can like set z equal to xy and then say that, oh well, z is approaching to 0, right? In this case, it actually works out like really good, because the only way for z to be approaching 0 is that one of these should be approaching 0. So yeah. Question 11 is find this limit. I don't know what's going on. So I can just substitute stuff in that, right? I mean, like, the quotient rule says just take the limit of the up and the down and then divide, and this does exist. It's some finite number over and finite non-zero number, so it's perfect. And on top as well, it's just some number, so who cares? X square plus y square just turns out to be like 1 plus 1, which is 1, which is 2. So it's 2 and then 2 times xy minus 1, I suppose, plus yz, which is just 1 basically. This is really bad. Minus 1 by 2. I have no idea what am I supposed to be like doing exactly. Am I supposed to prove this like more formally, the epsilon delta definition or something? I don't know. I'm just gonna use the quotient rule and say it's a thing. So call it a day. Find this limit. It tends to pi 0, 3 z e power e to 2y cosine of 2x. So well, x tends to pi, so just to have 2 pi, that's going to be 1. So that part is gone. Z tends to 3 and then y tends to 0, so it's just 3 basically. You don't have to, you just split the limits. What's the big deal about it? At what points? I mean, this whole stuff, there's not even a discontinuity, so I don't know what you're talking about. All of this is just like continuous functions multiplied together. Obviously the limit will exist. What is so special about this that you have to put in a problem? I think I'm supposed to be doing this in the epsilon delta way. But we were taught so many of these rules, why not use them, right? I don't know, I'm just gonna go through this like the old-fashioned JE style, just doing the limits and move on. At one point, xy in the plane is the function continuous. sine of 1 upon xy. Okay, so this is going crazy as x approaches 0 or as y approaches 0, right? Apart from that, it's like all continuous, so all such points. So question 13a is basically all xy such that x is not equal to 0 and y is not equal to 0, right? Yeah, everywhere it's like continuous basically. B is right. So this should be an and condition, so it's not just a comma, it should be like and. Yeah, B is g of x y equal to x plus y upon 2 plus, so 2 plus cosine of x, it can never be 0, so that part of like this becoming 0 is gone. And apart from that, it's all continuous, so x plus y is a continuous function, cosine x is a continuous, so 2 plus cosine x is a continuous function, and it's never going to be 0, so you're dividing a continuous function by another continuous function which can never be 0. What do you expect? A continuous function. So the whole like R2 plane, it's going to be continuous. Question 14. And what points x, y in the plane is this function continuous? Okay, so something is really amiss all of this. This can't be so easy. I just feel tricked. I feel like I was supposed to do it in a different manner. They are not telling me to be doing the epsilon delta definition, so I'm not doing it, but should I not be doing it? Anyway, question 14. At what points x, y in the plane is this function continuous? X1 minus 3, okay, this is first one. So this is like what, x square minus 3x plus, so 3 by 2 is like 9 by 4, 9 by 4, 9 by 4, minus 9 by 4 plus, so it's like, so it's not 8 by 4, so it's minus 1 by 4, so it's something like x minus 3 by 2 squared. That's the stuff. This is what rings are made of. Okay, so just x plus y, so we don't care about this really, we just care about this. So the only discontinuity points, or I could just factorize this directly. Yeah, I could have just done that directly. Why did I do so much of? There's no point going so like doing so much of things. So it's just this. So it's at x equal to 1 and x equal to 2 where you have messed up stuff happening. Otherwise you're okay. So 14th. So everywhere such that x is not equal to 1 and x is not equal to 2. Okay, go on. I guess that is the way it is, right? So at 1 it's certainly like not continuous. Everywhere else it is. Like no matter what you do, the like every sided limit is the same. So yeah, at 1 it's not. At 1 it's simply not. And at 1 it's not even defined, so how do you make it at 1? Okay. At what points in space is this function continuous? Whenever you have z is bigger than x plus y square plus 1. Right. Which is what region? What sort of a region is that? It's bigger than that. Set x, okay, at 0, 0 something like that would happen. I suppose it's more like x square plus y square is less than z minus 1. That's a better way to see it. Yeah, that should happen. So z cannot be 1 or anything less than that for that matter, because it's a square. So what does that mean? That z is strictly bigger than 1. And I just like say all x, y, z such that this condition. I wish I could. Hey, why can't I? I can actually. We just want to give all the points where this happens, right? Yeah. Oh wait, okay, that's not even question 14th B, that's question 15th B. Or what? What was that? Oh, that was question 16th A, sorry. I really just skipped to something else. Question 14b. 1 upon, seriously, what the hell? Is this function continuous? Amazing. So whenever x minus y is approaching 0, we are messed up. So x minus y should not be 0. That's the only condition. And then it can be anything. You just have a value. Easy, right? What happens when y is 0 but x is tending to 0 as well? So it's at 0 0. No, this doesn't work. That doesn't work. Yeah, that doesn't work. I see. If y is negative, this thing actually, that actually works out once. If y is negative, you are good. If y is positive, stuff might happen. I mean, yeah, sure. So it's all x, y such that y is not equal to x square. That's pretty much the thing, right? So basically, you just have this region y equal to x square. This whole parabola, it's not defined. I mean, the function is not defined there. Everywhere else, it's defined. It's okay. Question 15. H of x y z equal to x y sine of 1 upon z. So for x y is nothing to worry about. Sine of 1 upon z. So z equal to 0 is not allowed. So all x y z such that z is not equal to 0. So z could be anything. Z could be anything, frankly, and you would have a sign, so whatever. But z cannot be 0. D is 1 upon x square plus z square minus 1. So y can be anything, sure. What's the condition? The only condition is x square plus y, the z should not be equal to 1. I don't get it. Why am I even doing this? Such that, so x square plus z square is not equal to 1. So the spaces where this is discontinuous, you can graph them. Maybe that's the point. Over here, this would be z not equal to 0. So when z is equal to 0, just the xy plane. So we just have this xy z. So z equal to 0, which is being this whole plane. It's discontinuous there. But here it says xy plus z square equal to 1. So it's some sort of a circle in your xz plane. Or I should say cylinder. So this cylinder this thing is not allowed, it's discontinuous there. Okay, C. There's no C. Question 16. At what points x, y in space is this function? So that's where we did the thing. So when is this function continuous? Natural log of z minus x square minus y square minus 1. Clearly it has to be the domain, so z minus x square minus 1. But that has to be positive. And then it's actually continuous. You don't even have to worry. So z is bigger than x square plus y square plus 1. Easy. Yeah, pretty much. These are the points. Not gonna graph that. Not gonna do anything because I don't see a point. What about this stuff? 1 upon z minus square root of x plus y square. So x plus y square is always going to be, square root of that. That's going to be defined all the time. So that we don't have to worry about. So the only thing is z should not be equal to that. So z should not be equal to square root of x plus y, or I should say z square is not equal to. Yeah, actually it's a positive thing, right? So it can be negative. That's not a problem. It should just not be the positive version, right? Okay. Cool. Yeah, I suppose this is okay. At what points? Hey, so did I use square root somewhere else and then I made a messy thing? What did I do for question number 1? Yeah, I guess I did it correctly. And question 3. I guess I did it correctly actually. Just move on. Question 16 is, at what points is in space is the function continuous? We did that. Already did that. B is also done. Question 17. At what points in space? Just stop this. Just put everything in a single section for convenience, right? Is the function continuous? Why do you have to break it into so many different questions in that case? Like, you could just put it in a single section. No, it's all the same repetition. Square root of 4 minus x minus 1. Okay, sure. When it's, you know what, I'm not even going to like really do anything, because above that it's not defined. That's the only problem. It's not in its domain. Otherwise it's like it's continuous everywhere. I don't see the point. Yeah, I don't see the point. It's just the sphere, solid sphere. Even the boundaries are included. What's the big deal? H of x, y, z equal to 1 upon 4 minus. So what should happen is, like, 4 should not be equal to this, and the same time x plus y plus 9. This should be bigger than or equal to 9. At the same time, x plus y plus z squared, this should not be equal to square, that's like 16 is equal to this stuff, 25. So the r equal to 5 sphere is not allowed, and then all of these spheres more than 9 are in fact allowed. Cool. So B is done. Question 18. By considering different paths of approach, show that this function has no limit. Minus x upon square root of x plus y square. So shouldn't be too hard actually. Let's just consider the case where, like, so okay, wait, what? So as what? I'm assuming as x and y both tend to 0, 0. Yeah. So if we just say that x is set to 0 and like y is tending to 0, right? So consider the path. So path 1 is that your x of t is equal to 0 and your y of t is equal to t. So then as t tends to 0, basically your xy is tending to 0, your f of xt yt, that will just be like 0, obviously. Yeah, because it's like definitely 0. That's the thing. Okay, part 2. Part 2 is, let's just say that this is not going to work out. Square root let's just take the line y equal to, okay, let's actually take this thing. So we'll just say x of t is equal to, you know, t, and y of t is also equal to t, which would mean, yeah, it means it tends to 0, 0. Basically, limit as t tends to 0 of f of x of t, y of t. I mean, if it were to exist, this should be the same thing as the limit as x, y both tend to 0, right? So this would just be made independently. But what is this? It's just the limit, so negative limit as t tends to 0 of t upon square root of t square plus t square, which you guessed it, is just 2 magnitude of t. So in fact we can just take the limit as t tends to 0 plus, because it should still be the same value, so it's not a problem. But taking it 0 plus means that we can simplify stuff. So this would just be the same thing as 2t, right? So this would just be like negative 1 by 2, which is not equal to 0. So by different approaches you can see it doesn't work out. Question number 19. by considering different paths of approach so that this function has no limit. I'm just really tired of all of this. Why do I have to do this? Okay, so path 1 is, you just have I just set y to be equal to 0, so it just becomes t comma 0. Path 2 is, so as it's like t comma 0, it just becomes x, so basically like approaches 0 pretty much. And let's just have x equal to 0, so 0 comma t, and then it approaches 1. So this gives 0, this gives 1, and you can see these are not equal. 20. Should we show that this function has limit 0 along every straight line approaching 0, 0. Along every straight line. It didn't say along every path, it's a different thing. But yeah, along every straight line. So we just consider y equal to mx because that's the only sort of line approaching. Sorry for that. That's the only sort of line that is actually going to be approaching 0, 0. If there's a plus c, this is messed up. So yeah, since y equal to mx, we'll substitute that in there. So yeah, y equal to mx or x equal to my. So these are the two sorts of lines which you could be having. So consider y equal to mx. What do you get? You say like 2x squared, and then mx is like mx cubed upon x power 4 plus mx square which is like, hey, something is really messed up about this. I should be square anyway. Okay, so which is like what, 2mx upon x square plus m square. So yeah, right, which is in fact approaching 2m upon m square times 0, so that's actually just 0. So yeah, that's approaching like that. And then what about if you put x equal to my? Then this just becomes 2m square y cubed upon m power 4 y power 4 plus y square. Just divide by y square, so just 2m square y upon m power 4 y square plus 1. So once again, as y tends to 0, this would tend to 0 if your m is a finite quantity, and one of these will be a finite. So yeah, question 20 is done. Question 21. Okay, that was it. That was the whole tutorial. Seriously. Let f of xy be this piecewise. Find each of the following limits or explain that the limit does not exist. Okay, limit as xy tends to 0, 1 of f of xy. So when you set x to be, wait a second, right, 0, 1. Okay, so let's just first graph out what this function is. So when y is bigger than x power 4, so x power 4 will look something like this, I guess. 0, 1, it's actually going really bad. So it's something like this. That's your y equal to x power 4. Okay, sure. So everything above that, it's 1. Everything below y less than or equal to 0, it's 1. And so these boundaries are actually inclusive of that, in fact, and everything else is like 0. So all of this is just 0. So this whole block is there, this whole block is there, but this is 0. Sure. So we want to show that at 0, 0 the limit does not exist, which is true. Consider this path. Just consider like y equal to half x power 4, right? So walking along that path, which I don't know how I would say this. So it's something like x comma half x power 4. So or if we want to be more specific, it's like t comma half t power 4. So it's easy to see that y is less than x power 4, right? So that would mean, and y is like bigger than 0. So yeah, I mean y is strictly bigger than 0 because t is not yet 0. So what that means is it's going to be 0 constantly. So then the limit as t tends to 0 of this f of x of t, y of t, that's going to be equal to 0. But at the same time, like if you approach it from up, like from upwards, right? So you just set x equal to 0, y equal to 1. Y is always going to be equal to 10 x power 4 that way. So start from 1, so you just go downward. You have 1 all the way through. So yeah, it's going to be 1 that way. So it does not exist. Yeah, I just proved it for 0, 0. That's not what I wanted to. Okay, I did C part first. This is C. Oh, sorry, this is 1. A is as y tends to 1 and x tends to 0. So in which region would it lie? I mean, clearly, like y cannot be less than or equal to 0 if it's tending to 1, and y is necessarily bigger than x power 4. So it's strictly lying in the y bigger than or equal to x power 4 region, right? 0, 1 is this point. What does that mean? It's 1. What about 2, 3? Three is not bigger than x power 4, which would be too much, and y is not less than or equal to 0, so it's 0, strictly 0 in fact, and it's not in the boundary, so it's okay. 22. So I found it or explained that the limit does not exist. Sure, I did not prove that the limit does exist. That wasn't my job. Question 22. Does knowing that 2 measure of x, y, left minus okay, whatever this thing is, tell you anything about what? Give reasons for an answer. X y minus x squared y squared upon 6. Hey, so you're saying this is something that is true all the time? Saying it's less than 2xy. You just Taylor series expanded, didn't you? Yeah, you did. That's how you want it. Okay, so sure, that makes sense. That's our theta power 4 thing. Taylor series expansion, that's what this guy did. Sure. Okay, why did you get a 6 over there? I have no idea. Is that intuitive? So you have theta power 4 upon 4 factorial, so that makes sense. So you would have a 3 over there. So does this tell you anything about this? I mean, yeah, sure. So as right. So just divide by a magnitude of xy. What does that give us? It just gives us 2 minus is less than 4 minus 4 cosine upon magnitude of xy. And this is like less than 2. So as xy tends to 0, this tends to 0 as well. So the limit is actually 0. Sandwich theorem. Right? Yeah, because these two are approaching 2, so this limit is also approaching 2. So this works out if you're not going along the path where x is 0 or y is 0. But what about the path where it is like that? So if we set x to be 0 completely, well then this is does not even make sense. Yeah, it is not in the domain of this function, so it's okay. Can't go along the path since not in domain, right? That makes sense. Question 23. The exercise below gives a function f of xy and a positive number epsilon. I have no idea what's going on. But shouldn't it be something like, you set x to be 0? Okay, that actually is messed up. It's really messed up. You probably don't want me doing that. So if none of them are 0, you can use this inequalities and show that, oh, this does exist. But okay, never mind. Exercise below gives a function f of xy and a positive number epsilon. Now, what I'm concerned with is that would there be any other path where you approach this point 0, 0 and then it gives you something else? And I'm guessing not. If it's defined, then xy has to be bigger than 0. Exercise below gives a function f of xy and a positive number epsilon. Show that, okay, epsilon is 0.03, it's an actual value. There exists a delta such that for all xy, right, this being bounded by delta, so it's basically 0, 0. xy is approaching 0, 0, right? The usual epsilon delta definition. So you have square root of x plus delta, and this is tan square x plus tan square. What the? Okay, so square root of x square plus y square less than delta, that implies x is less than delta and at the same time y is less than delta, right? So what does that mean? And since tan square is an increasing function, so what this implies is that tan square of xyz is less than or equal to, so you are setting z equal to 0 in any case, right? So that thing is less than or equal to, not even equal to, it's strictly less than. So it's a monotonically increasing function without the slope ever being 0, right? So this is actually going to work out. So what do you have? You just have, okay, so 2 tan actually is kind of going to 0, sure. Can you really say that? But we know it's an increasing function. Yeah, fine. I mean, not from the fact that slope is not going to 0, but we know as a fact that this is an increasing function. So what that implies is this will be less than tan square delta. So tan square delta plus tan square delta plus 0, which is just 2 tan square delta, right? And so we want this to be epsilon. So basically we use delta is equal to epsilon by 2 square root of that tan inverse of that. So actually use any delta which is less than or equal to this number and things work out. Yeah. So in this case it would just be something like tan inverse of square root of 0.03 by 2, which is like, I have no idea what this number is, but okay, now the question is how do you find this number? Oh, this is pretty easy. I know a way. I know a perfect way. Like this. What do we want? We want 0.015 square root of that. I think that's 0.015, yeah, sure. And then tan inverse of that. We'll have to import it. We'll just set it to something so it's executing that. So from 1 by anyway, so arc tan of this number, that's this thing 0.015 So I'm just going to use 0.007. That works out. Use delta equal to 0.007. Works out. Okay. And yeah, that's pretty much it. So we are done. Okay then. Oh, so and I'm saying x is less than delta, y is less than, I'm assuming that x and y are positive. So what I should pretty much be saying is something like this, but you get the gist of it, right? That since it's a square, it still works out, right? Tan square is an even function. It doesn't matter if x is negative or positive or whatever. So yeah, see you guys in the next video.